I'm in one of the most geologically extraordinary places on Earth, Yellowstone National Park.
You may know Yellowstone for its geysers, hot springs, and wildlife. But underneath all that is a supervolcano so powerful it reshaped the North American continent.
In this video, we're going to walk through the geologic history of Yellowstone,
from billion-year-old ancient crust to the current state of this active volcanic system. And stick around because I have a very exciting guest expert that will help me explain the geology of this amazing region.
To begin, we have to go back over 2.5 billion years ago, long before the hotspot that caused the Yellowstone region to start being volcanically active arrived, which I'll explain later. But it's at this time, over 2.5 billion years ago, that Yellowstone's roots were being laid.
The North American craton, or the ancient stable interior of the North American continent, also sometimes called the Canadian Shield or Laurentia, formed during the Archean eon, between around 4 to 2.5 billion years ago.
The oldest rocks in Yellowstone are metamorphic gneiss and schist that are part of this ancient crust. Over time, and by time I mean hundreds of millions of years, this ancient crust was covered by shallow seas.
And then uncovered and covered again, and so on as sea level and the continent's topography changed. And when this region was covered by shallow seas, thick sequences of limestone, dolostones, and shales accumulated. In fact, you can still find these sedimentary rock layers exposed in northern Yellowstone.
But during the Mesozoic and Cenozoic eras, so over the last 200 million years, the western edge of North America underwent
major tectonic collisions and mountain building events that reshaped this region.
Although Yellowstone doesn't seem like it's that close to the western margin of North America today, it actually used to be much closer.
Recall that the stable interior of the continent, the craton, is actually what North America used to look like. Then, over hundreds of millions of years of plate tectonics, the craton accumulated more land along its western margin due to what we call accretion. As other continental landmasses and island arcs slammed into this margin, much of this crustal material accreted onto the continent, essentially expanding the size of North America over time.
These mountain building events deformed and uplifted this region, laying the structural groundwork for what would become Yellowstone. And now to the part I know you're all waiting for, the arrival of the hotspot. For those of you who don't know, Yellowstone's volcanic activity is driven by what's called a hotspot.
Hotspots are areas of Earth's mantle from which hot plumes of magma rise upward, forming volcanoes on the overlying crust.
Hotspots are unique because they can be kind of random in location compared to volcanism that occurs along plate boundaries.
The textbook example of hotspot volcanism is Hawaii. The Hawaiian Islands don't each have their own mantle hotspot. There's just one hotspot in the mantle that is responsible for the entire chain of islands because of the migration of the Pacific Ocean plate over the Hawaiian hotspot. So while hotspots within the mantle do not migrate, tectonic plates, which lie above the mantle, do.
The same concept goes for the Yellowstone hotspot. So where do we see evidence of this hotspot migration, and when did it finally reach Yellowstone?
Well, for this, let's ask our guest expert, Shawn Wilsey.
Yeah, so the Yellowstone hotspot track runs through southern Idaho. It's what we call the Snake River Plain, and it's a low area. We can find deposits from these big explosive eruptions throughout the Snake River Plain, but we don't find them so much in the Snake River Plain because they've been covered with basalt. So there's this chocolate frosting of lava that obscures it. But when we look at the margins of the Snake River Plain, that's where we see the rhyolite deposits, the ash, the explosive products from these events. And we see a nice steady progression of ages from about 16 million years near the southwest corner of Idaho, getting progressively younger until you get up into the Yellowstone area where they're as young as 600,000 years old.
Yeah.
And just as a quick aside, the chocolate frosting that Shawn is referring to is younger basaltic lava flows that have covered much of the Snake River Plain long after the rhyolitic lava flows and tuff that came from the hotspot volcanism millions of years ago along this track. Shawn actually took us to see Shoshone Falls in Twin Falls, Idaho, where you can see the rhyolitic cliffs underlying the much younger basaltic frosting. And he also showed us the beautiful rhyolite cliffs at Mesa Falls, where you can actually see a younger basaltic flow come in on the other side of the river, which apparently actually moved the river when it was deposited around 29,000 years ago. But this rhyolite, the rhyolite cliffs here at Mesa Falls, actually come from the same 1-million-year-old eruption from the hotspot volcanism that deposited the rocks that we're looking at here at this road cut. So we'll get back to this road cut now and Yellowstone hotspot volcanism, but if you are curious where the basaltic lava flows came from, which are much younger than the hotspot volcanism, you can check out Shawn and I's Craters of the Moon video, which is a video about one of these places where we can see tons of this basalt. And just another quick note, you have now heard Shawn and I refer to rhyolite and basalt several times, so I feel I should quickly explain the difference. In the most simplest of terms, basalt is oceanic crust and rhyolite is continental crust. It's not that simple, but for the purposes of this video, that's what we're going with. So, for example, the Hawaiian Islands are basaltic because that hotspot lies under oceanic crust, whereas the volcanic rocks produced by Yellowstone's hotspot are rhyolitic because the hotspot has to melt its way through the continental crust that lies above it. So now you may be wondering, how the heck did the younger basaltic lava flows that we just referred to even form smack dab in the middle of a continental plate? And trust me, I was wondering that before I came here on my trip as well. Thankfully, Shawn explains that in our Craters of the Moon video, so you have to go check that video out for that. But for now, back to the Yellowstone hotspot.
So at these places where we see kind of the track and the movement of this hotspot under the plate, well, really not the movement of the spot, but the movement of plate over the spot.
Right.
What kind of things would people coming out here to look for? What would we look for?
Yeah, so it's tricky because these eruptions from Yellowstone are really on a scale so different from what we typically see like at a place like Mount St. Helens. And the rock types are a little different too. They tend to be very hot eruptions. Enormous quantities of ash are generated. In fact, in some places there's so much ash and so much heat that when that stuff is in place that it actually remelts and remobilizes and it flows and bends on itself. Yeah. And so once you get an eye for it, they're pretty characteristic. The rocks can sometimes look dark if there's a lot of glass in it, so it's easy to mistake it from a distance as basalt until you kind of get an eye for it. Okay. Other times you might see light-colored ash, like almost white ash, which is, you know, a little bit more obvious. So there's a lot of diversity in these rocks, but you know, chemically they all look the same. Yeah. And you really could start at those 16 million year old rocks, look at those, you know, blindfold yourself and, you know, fall asleep and then have someone take you to another spot on the hotspot track and think you're looking at the exact same rocks, but you've changed locations, you've moved up the track into younger rocks. And so they're really characteristic, but they speak to just how explosive and massive these eruptions are.
Wow. How do we know from the rocks that they were so explosive?
We can look at the quantity of ash, and from that we can start to figure out how big the eruption is. We sometimes look at volcanoes like that on this scale called the Volcano Explosivity Index, VEI. And so the bigger that number is, the bigger the eruptions are. So these Yellowstone eruptions through the Snake River Plain over time have been just massive. Like there's nothing in human history that is a comparable analog to the scale of these eruptive events.
Why? Why so big? Why so eruptive?
It's just an incredibly productive system when you have the hot spot and that basalt melting and partially melting all that continental crust and generating a new batch of rhyolitic magma, just enormous quantities of rhyolitic magma, gases trapped in it, and so you end up over time getting these very hypercharged explosive events.
Oh my gosh, that's so cool. And so now we're here at this place we're not in Yellowstone, but we're along the track.
Right.
And we've got these really, really super light
like
pumice-like rocks. So what is this telling us?
So these are chunks of pumice, and these are interesting because you can actually see some crystals in here. There's actually some quite large, almost up to centimeter size crystals of quartz and a feldspar mineral called sanidine. You can also see that there's almost like stretch marks in the vesicles and the gas bubbles. That speaks to the viscosity of this magma. It was so sticky and pasty as the gases were trying to escape from this material. They were being stretched out. The big crystals tell us that before this erupted, there was some crystallization that had taken place. So there was crystals forming in the magma body before the eruption. But this outcrop here has a really interesting story because this kind of walks us through this event. So this was an eruption that took place 1.3 million years ago. We're just outside the Henry's Fort caldera. Of the 3 most recent Yellowstone eruptions, this is the smallest, but it's still huge by any other standard. And so what we have here at the left side of this outcrop, it's a little hard to tell because there's so much cover here, but you can see a lighter kind of gray kind of popping up there, almost like a white material. And that's ash, mostly just disaggregated ash with a lot of these crystals in it. And that represents the initial phase of this eruption. So basically the vents being cleared, the eruption has begun, ash is coming out of these vents in the ground, and it's raining down on the landscape. So that's sort of like the first phase I see when we look at this. And then if we look at sort of this next section of material here, this is where you see your chunks of pumice coming out. There's pieces of pumice embedded in this material here. This represents, okay, now we've really tapped into the magma chamber. The gases are expanding and it's throwing these out. These are airborne chunks of pumice that are being ejected from the vent, that are being dropped onto the landscape after this initial kind of ash-rich vent clearing phase.
Does pumice like solidify in the air or when it hits the ground?
It's probably pretty solidified while it travels through the air, and it's carrying the crystals with it. The gas bubbles have formed and solidified as well. So basically, at this spot 1.3 million years ago, there's pumice blocks that big, bombs, I guess you could say, just raining down out of the sky.
Pretty scary.
Pretty rough scene. And then just when you think the worst had come, if we walk down a little further this way, those pumice blocks, you can kind of see them in here. Now you're starting to see different chunks of them in here. And as we get into this section here, this is all sitting on top of it. Everything's dipping a little bit to the south. Now we're looking at what we call tuff. So this is consolidated and welded ash. These are from the pyroclastic flows. So this is basically an avalanche of ash that has spilled over the caldera rim that's racing down towards the valley here at maybe 100, 150 miles an hour, who knows how fast. Super hot, just incinerating everything in its path. And it has enough heat and mass to it that it's actually welded together pretty well. And this continues all the way to the end of this road cut.
Oh my gosh. Wow.
So this is just when you thought the worst had come, this would be, if you could dodge the pumice blocks, this would be this huge cloud of ash that would be, that would be the end of the end of the story right there if you were here.
So do most of the places along the hotspot track that you can see this kind of stuff, does it all look like this?
In places it does. It's nice here because it's younger and more preserved, and we're on the flank of this caldera that's still preserved. As you go down the hotspot track, all that chocolate frosting's obscuring it, so we don't see it in as good a detail as we see it here.
Right.
And in other places, if you're within the caldera where there was a lot more ash and a lot more heat, sometimes this stuff gets really well welded together and it forms some other rock types. But I like this cut in this location because it kind of shows the progression of this eruptive event from the ash fall to the pumice blocks falling out of the sky to now we're into the pyroclastic flow material.
Oh, wow. And many people might assume that any volcanic rock and volcanic activity that you see in southern Idaho is from this hotspot track, but there's the younger chocolate frosting that's a little different. And so go check out our Craters of the Moon video if you want to hear more about that. Once the hotspot arrived beneath the Yellowstone Plateau, there were 3 major caldera-forming eruptions.
The first and largest was Huckleberry Ridge around 2.1 million years ago, forming the Island Park caldera. Second was Mesa Falls around 1.3 million years ago, which was smaller but still enormous. And third was the Lava Creek eruption around 640,000 years ago, which was the most recent and formed the current Yellowstone caldera. The Lava Creek eruption blasted over 1,000 cubic kilometers of ash into the atmosphere, covering large swaths of North America. Ash from this eruption has been found as far away as the Gulf of Mexico. And afterwards, the land collapsed into the emptied magma chamber, forming the giant 70 by 45 kilometer wide caldera we see today.
But the activity didn't stop there. The caldera refilled with magma, creating uplift zones like the Sour Creek and Mallard Lake resurgence domes. And since then, numerous lava flows have erupted and filled parts of the caldera. But is this supervolcano still active today? Is it getting ready to erupt soon? How would we even tell? Well, let's get back to Shawn for this one. So we are now in the middle of the Henry's Fork caldera. And so, you know, this is quite a huge extent of like what happened here, the explosive eruptions. But how likely is that to happen again now in the Yellowstone caldera?
Probably not as likely as a lot of people think, right? I think Yellowstone is an impressive place. The scale of its eruptions kind of like overwhelm the senses and defy imagination. But when we really look at how often these events occur with respect to a human lifetime, they're incredibly infrequent. In order to have a system like that completely primed and ready to erupt and have a eruption on that scale, you're looking at, you know, recurrence intervals or spacing of like hundreds of thousands of years. And we had the last one 600,000 years ago. And furthermore, we have current research that suggests that the magma that's underneath Yellowstone, the actual magma body that feeds these eruptions, is at least half of it's crystallized. So it's not even what we would call eruptible magma. It's basically 50% or so like solid crystal particles, and in those interstitial spaces is the actual melted rock, the magma. And so it's not even at a stage right now where it could erupt. And we think these things take a long time to evolve. So yeah, not anytime soon.
Not anytime soon.
Don't lose any sleep over this.
So as a volcano, it is technically defined as active?
Yeah, I mean, it's depending how you want to define it. Certainly when tourists go there and they see the geysers and the hot springs and the mud bubbling out, it feels very alive, it feels dynamic, and it feels active. But that's just the hydrothermal system. That's just the shallow water, groundwater system that's heated by the hot rock below. And that's really not an indicator of what's going on at depth with the volcano itself. We get earthquakes there, of course. And so, yeah, I think calling it active feels right, but it depends on how you define what an active volcano is. There's certainly a lot of other volcanoes in the western U.S. much more likely to do something sooner in our lifetimes than Yellowstone.
Okay, so good to know. Nobody needs to worry too much about this.
I think death by Yellowstone should be at the bottom of everyone's bingo card, for sure.
Good to know. Yeah. Good to know. And so the last question is, if there was something like an impending eruption gonna happen at Yellowstone, or really any volcano, what would be the signs that we would look for? Yeah,
so we'd expect to see, I mean, there'd be a lot of buildup for a volcano the size of Yellowstone to have a big eruption like we've seen in the past. We'd have to see earthquake swarms, especially, you know, in certain regions around the magma chamber. We'd expect to see the ground deforming, and we see that a little bit today. We see it rising and falling, but we'd want to see an accelerated rate of ground deformation, maybe accelerated rate of gas emissions and the concentration of those gases coming out of the ground. So you need really like a convergence of lots of bits of monitoring data, all indicating that the system is priming and ready for an eruption. And that would just, you know, it's a lot of things that happen over probably several weeks, if not longer. And we just aren't seeing that yet. So we're quite a ways from that, we think.
Absolutely. And the hydrothermal activity is different and not necessarily directly indicative of the volcanic activity.
It's operating separately. It can have its own earthquakes. We had a hydrothermal explosion about a year ago in the park near a tourist area. And so that's a different system than what's happening at depth with the magma itself.
Yeah, absolutely. And I'm going to talk way more with Cameron Fetter, my other friend, ranger there now. And we're going to talk way more about the difference between geyser eruptions and actual volcanic eruptions. So stay tuned for that video. Well, thank you, Shawn, so much for coming on and sharing your knowledge. And he has so much more about Yellowstone on his page. You can dive way deeper. You can get his books about Idaho geology and go check out all his stuff. Links are below. There were 3 major super crap, and since then, numerous lava flows have filled parts of the There were three major Damn it. So, Shawn, we are now in the middle of the Henry's Fork. Wait, I already forgot. Fork.
Cut.
Hundreds of millions of years, this ancient crushed. There were three major. Damn it.